Hello students, welcome to the EPG Pathsala. I am Professor D. Vel Murugan from Center of Advanced Study in Crystallography and Biophysics, University of Madras, Gindi Campus, Chennai, in which I was a former head of the department, and now I am in the same department working as the University Grants Commission Basic Scientific Research faculty. Today, I am going to talk to you and explain you in the module dealing with the determination of the three-dimensional structure of small molecules using single crystal X-ray diffraction. As you know, we have more than 8 lakhs molecules deposited so far in the database known as Cambridge Structural Database. So we are going to learn how the molecular structures can be determined using single crystal X-ray diffraction, which forms a part of the paper biocrystallography. So, students, let us see what we are going to learn in this module. First of all, I am going to explain briefly what is meant by phase problem, which is a bottleneck in X-ray crystallography, and I am going to deal in depth what do you mean by direct methods. Why I am telling in depth means direct methods have been honored by giving the Nobel Prize to the pioneers of this branch of crystallography, namely Professors Hoffman and Karl, who developed these methods from 1950s onwards, in spite of they have been subjected to severe criticism by the physicists all over the world. And finally, the formula developed by them in 1950s have been proved by the wife of the other Nobel laureate, Professor Jerome Karl, namely Professor Isabella Karl, when she applied the formula to determine the structure of a dipeptide, and thereafter the same group of scientists who have been opposing them vehemently started writing computer programs, and the first automated programs to use direct methods to solve small molecular structures came in the year 1972 from University of York, England. That is why you are going to learn an important topic here, direct methods. I am going to teach you, because I did my postdoctoral work on the Nobel laureate Professor Hoffman for nearly 4 years. I love to promote this subject to all of you. Now I'm going to also teach you the steps in the three-dimensional structure determination. Of course, we are going to discuss about the versatile package being used by all small molecule crystallographers, namely the Shellax S, which is used for structure determination, and Shellax L, which is used for least squares refinement. And all these programs have been released by Professor George Sheldrick from Göttingen, Germany, and these are all incorporated in the WinGX suite. And we are also going to discuss about the program known as RTAP, which was released from Oak Ridge Thermal Ellipsoid, which is abbreviated Oak Ridge Thermal Ellipsoid Plot. Of course, Oak Ridge is the name of the place in Tennessee State, United States of India. It has been released by Johnson. The three-dimensional crystal structure analysis of molecules at the atomic level could be possible only if, in addition to the experimentally measured intensities, the phases of Bragg reflections were known. The non-availability of phases from a diffraction experiment is called the phase problem in X-ray crystallography. So unless you solve this phase problem, we cannot do the Fourier synthesis, namely calculation of electron density, in which both amplitudes and phases occur as the coefficients. Nearly 70 decades ago, that is the 40s, 30s, 1930s, no, crystal structures have been solved only for molecules containing lesser number of atoms in the unit cell. Most of the times, intuition and expertise plays major roles in arriving at the molecular structures, and they took many years to solve the structure of molecule containing even up to 10 to 20 atoms, because those days there were not any correct and systematic procedures available for solving the phase problem. No computer was available, no electronic devices were available to automate the data collection, everything and so on. Everything they did manually. In 1950s, Professors Herbert Hoffman and Jerome Karl from US came out with some drastic assumptions like the electron density should be everywhere positive, and the real crystal with continuous electron density can be assumed to consist of capital N non-vibrating point atoms. Now, based on these assumptions, They said they got a formula connecting different types of special combinations of phases called structure invariants and structure semi-invariants, from which we can do a sort of refinement known as tangent formula refinement to obtain individual phase values. Now, since they assumed as a point order model, they converted the nominal structure factor amplitude corresponding to spherical atom to that of the nominal structure factor amplitude mod EHKL corresponding to point atom by simple formula, and they did a synthesis called EMAP, where the Fourier synthesis coefficient is replaced by mod EHKL. And when they told this, based on this assumption, they can get a molecular structure roughly, the other scientists in the world, they didn't accept it because these assumptions were not accepted at that period, as they are all against the laws of physics. How can you consider atoms when you're having different number of electrons, like carbon containing 6, nitrogen 7 and oxygen 8? How can they consider all the atoms to be point atoms? Then how will you distinguish between these two atoms? Another thing is, the solid state physics tells you that any atom is not at rest. Atoms do vibrate, lattice vibrations. Being so, how can you consider non-vibrating atoms? But this opposition didn't trouble, because they know that it is going to work, because Hoffman is a mathematician. He kept on deriving the relations for so many space groups, and they first solved the phase problem for centrosymmetric case, which is simple. Then they proved how it could be extended to non-centrosymmetric case also. Later on, other people from different countries like different David Sayer, Professor Wolfson, Cochrane, and Professor Jacob also from Italy. So many people joined the team of direct methods, and everyone has contributed. But major contribution, I can say, it has come from only these two pioneers, Professor Hoffman and Karl. Professor Hoffman and Karl, even though they worked together at Naval Research Laboratory, Washington, then Hoffman came to Buffalo and started Medical Foundation of Buffalo, and he was there until his death. And these two people, Hoffman and Karl, insisted that based on their assumption discussed above, they would simply produce a model which can later on be subjected to adjustment of positions and thermal factors of each atom, leading to the reality. Even then, it has not been accepted. In spite of their convincing arguments, eminent scientists in the globe didn't accept the formalism called direct methods, which are the mathematical methods or the probabilistic methods, using which directly from the measured intensities, phase information could be obtained through some selective phase relations called structure invariants and structure semi-invariant. When I say direct methods, don't think that it is a very simple procedure, because that phrase directly is a no. We have books after books written on direct methods by these pioneers. Direct means that directly we can use the measured intensities to arrive at phase information, which can be used after doing phase refinement in the formula of the Fourier synthesis to obtain rough model. Hoffman and Karl, they came out with certain assumptions for easier simplification of the mathematics used in the probability formula, namely, the real crystal with continuous electron density can be replaced by non-vibrating point atoms numbering to capital N. But this was subject to severe criticism by the physicists, telling that how can an atom can be considered as stationary. As per your solid state physics, atoms have to undergo vibration. And also, when chlorine, nitrogen, oxygen are there with different number of electrons, how can you consider all of them as point atoms? But the criticisms didn't trouble Professors Karl and Hoffman, and they had confidence in their methodology, and they worked out together many formulae for solving phase problem in specific space groups also. And a monograph authored by them titled Solution of the Phase Problem, Part 1, The Centrosymmetric Crystal, was published by the American Crystallographic Association in the year 1953 itself. These scientists later came out with a formula called tangent formula, which is the basis of direct methods, and this formula relates the known magnitudes to the desired phases through the phase relationships. It was only in 1966 Dr. Isabella Karl a famous peptide chemist, the wife of Professor Jerome Karl, proved that in a dipeptide case, the formula developed by Professors Karl and Hoffman could solve the structure. After knowing the success, the very same group which was objecting to the assumptions framed by Professor Hoffman and Karl started writing computer programs, because until that time structures have been solved by hands only, hand propagation. No computer was there, no calculator was there, everything they used manually. And the first program was released by the group headed by Professor M.M. Wolfson, and Professor Peterman also took an active part in that. These are the professors from University of York, England. The program name was Multan. In the program name Multan, M-U-L, mul means multi-solution tangent formula. Tan means tangent formula, mul denotes multi-solution tangent formula. If we look at the direct method, which we are going to see later, these procedures are multi-solution in nature, and tangent formula is used to define the phases. So instead of honoring straight away these people, the direct method pioneers, they just honored them by releasing the program Multan. Many scientists all over the world have also contributed to the field of direct methods from different countries, but the contribution to this field by Professors Karl and Hoffman was not only enormous but also continuous. During 1976, an Italian scientist, Professor Giacavoso, came out with a representation theory which has generalized most of the formula derived by Karl and Hoffman, and he has published a textbook just consolidating whatever work he has done in this direction. The difference between the assumptions made by Karl and Hoffman and Giacavoso is that one assumed the crystal structure to be fixed, that is, atomic coordinates are fixed, and the reciprocal lattice vectors HKL are assumed to be random variables, and the other assumed the reciprocal lattice vectors to be fixed, the Mendel indices HKL, and considered the atomic coordinates as the random variables. In either case, the H dot Rj defined as Hxj plus Kyj plus Lezj will be the random variable. If you look at this formula, if HKL are fixed, then if Xj, Yj, Zj are random variables, again H dot Rj is variable. Because of this, your structure factor itself is a variable. Or nominal structure factor itself becomes a random variable. Or if you fix Xj, Yj, Zj and assume Hk as random variable, again H dot Rj becomes random variable. So by virtue of the above, the structure factors involving this quantity will always be the random variables. For easier mathematics and to avoid the dependence of atomic scattering factor on sin theta by lambda term, the normalized structure factor magnitudes representing point atom model were used by Professors Karl and Hoffman. At present, nearly 8 lakh small molecule structures have been determined, and more than 99% of these small molecule structures are solved by direct methods only, and Professors Hoffman and Karl have to be saluted for this success. And most of the people now use Shellac suite of programs written by Professor George Sheldry from Germany. This is the most efficient package in obtaining three-dimensional crystal structures of molecules within the shortest time. If you look into the formalism proposed by Karl and Hoffman, they did a systematic way of overcoming the phase problem, and they developed a synthesis known as E-map, where the average of EH multiplied by e power minus 2 pi I H dot R over all the reflections will be equal to Fj naught over sigma 2 power half if R equals to Rj, and if R is not equal to Rj, this value will be 0. What it means is that only at the atomic side R equal to Rj, the map in the left hand side will have a non-vanishing value. At the other point, it is 0. So this is known as E-map. So this map can be calculated if you know the amplitudes of the nominal structure factor, which can be obtained from the amplitude of the ordinary structure factors corresponding to spherical atom. And only at atomic side, the synthesis of the right hand side is non-zero. On other points, it is 0. So now if you look at this equation again, the average is taken over H. Suppose we have n reflections. So if we take the real part and imaginary part after expanding the left hand side, we have 2n equations with you. And the unknown is actually n atoms are there. So n atoms, we have 3n positions unknown. And since we are using n reflection, each reflection we have to get the phases. So total number of unknowns is n plus 3n. but the number of equations available is 2n. So now what we are going to say you now is the phase problem while formulated in the way Hoffman and Karl did tells you that it is solvable in principle because it is overdetermined, because we have more number of equations than the parameter, or we have redundant system of equation. Let us see. You want to solve a structure containing total number of atoms capital N to be equal to 100. And for that, suppose you take 500 reflections as small n. Now, your 2n equations, 2n means 1000 equations you have. Unknowns is nothing but n plus 3n. That is, n is 100, 3 into n. Capital N is 100 means this will be 300 plus number of reflections 500, 800. So 800 are the unknowns, but you have with you 1000 equations. So first problem by using the above procedure is solvable in principle. This is how they formulated. Even then people didn't accept because of the assumption they made. As shown in the example just now, the number of equations 2n usually exceeds by far the number of unknown n plus 3 capital N. Though the problem, that is to determine the phases phi h, when only the magnitude mod h is given, that is the phase problem, is now greatly overdetermined in general. In other words, the phase problem is in principle solvable when reformulated in terms of fixed point atoms. Professor Hoffman and Karl introduced two types of special relations, phase relations called structure invariants and structure semi-invariants. They also proved that when origin is getting shifted, the magnitudes of structure factor remains constant and it is only the phase which changes. Although the single phase changes with respect to shift in origin, there are some special combinations of phases like phi of capital H plus phi of capital K plus phi of L, which does not change or which remains invariant when the origin is shifted, provided H plus K plus L equal to 0. When I say capital H, capital L, by each one of these I mean reflection with 3 serials. Capital H I mean H1, K1, L1 reflection. Capital K I mean small H2, K2, L2 reflection. And by capital L I mean small H3, K3, L3 reflection. And by telling H plus K plus L equal to 0, I add all the H serials, then K serials, then L serials. I get 3 subconditions for H plus K plus L equal to 0 as H1 plus K1 plus L1 equal to 0, H2 plus K2 plus L2 equal to 0, and H3 plus K3 plus L3 equal to 0. This possibility is possible because these Miller indices H1, K1, L1, H2, K2, L2 and H3, K3, L3 can be positive or negative including 0. So there is a possibility that H plus K plus L may be equal to 0. Now, this is the definition of such an invariant, a linear combination of phases which remain unchanged or invariant when the origin is shifted. There is another phase relation known as such a semi-invariants, which are the linear combinations of phases which remain unchanged when the origin is moved to within those permitted by space group symmetry. For example, if you have a two-fold symmetry, it is convenient to keep the origin on the two-fold axis. If you have a 2-1 screw axis, again it is convenient to keep the origin on the 2-1 screw axis. If two 2-1 screw axes are intersecting, it is convenient to keep the origin at the intersect point. Which means that when you talk about these symmetry elements, the number of origins possible become restricted. So within these restricted origins, when you talk about the linear combination, they remain invariant. That is why it is known as such a semi-invariant. The probabilistic estimates of these relationships have also been derived by them in many publications. Using these in the tangent formula along with known magnitude of nominal structure factors and doing a refinement, individual phases can be obtained for selected Bragg reflections having large E values. So now you know mod E values from experiment, then phases are known from tangent formula. You can do an E map to obtain the structure. So this is the principle of direct methods of solving molecular structures. Let us now look into the steps involved in the three-dimensional structure determination. Now, for the three-dimensional structure determination of molecules using single crystal diffraction, first of all, the first and foremost step is to crystallize the molecule to a dimension of about 0.2 millimeter on length, breadth and also thickness in the form of a single crystal without any cracks or clustering. So you are going to use this crystal only for the X-ray diffraction experiment, and we are going to collect the Bragg intensities. So the purification of the sample plays a major role, because the utmost pure compound will give good diffracting crystals, which will give good data, because we are using data only to produce model. So that is why compounds should be 100% pure. In the absence of electronic devices for measuring Bragg intensities, in earlier times, photographic methods have been used to measure the Bragg intensities of thousands of reflections, which are very, very complicated procedures, because all intensities in the X-ray film, when you develop, will be dark spots. You have to give some numerical values for each spot. Only the darkest spot you can give 100. But how to give numerical values for those numbers? So those days, density meter is not there, where you can scan the spots and get the intensities converted into area under the curve, and different curves will have different area. In spite of that, they have involvement and interest. No, they work hard, and instead of wasting 2 years, 3 years, after that only they were able to get the molecular structure. Even then they continued. For understanding the symmetry, they used oscillation and rotation photographs. So we have Weissenberg developed his camera called Weissenberg camera. It's nowhere being used, because now everything is automatic now. So they use oscillation and rotation photographs to and then after from the picture they used to understand the symmetry. There were Berger's precision camera. Then he used patiently, they estimated the Bragg intensities from the photographs after indexing everything. They used to have many layer photographs from the Weissenberg camera. Finally, those spots after indexing were estimated for the intensities. Later only, scanners came, and at present, powerful devices like charge-coupled devices and imaging plates are used for data collection. So within half an hour also, if you want to just see whether your molecule is there in the crystal or not, we can do fast data collection also. So this just tells you what are the hardship being faced by the crystallographers in 1950. This is a picture known as Weissenberg photograph, where the pinacoids and festoons are shown. Pinacoid is just like a straight line going, and the curved arc are known as festoons. So this is called a layer photograph, where a crystal is rotated and the film cassette is also having a translation movement. So this is how they scanned the entire film to obtain the Bragg intensities of all reflections coming out of the unit cell. Later on, they measured the intensity of the spots visually. So this is the reason why sometimes it became erratic, and also they have to do the Fourier synthesis, for which the trigonometric terms sine and cosine have to be calculated, for which there is no calculator at that time. In spite of that, because of their involvement and hard work, they have been able to do the structures. Of course, the total number of molecular structures determined were very small in number. As we have seen before, the first step involved in the three-dimensional structure determination is to crystallize the molecule and get a single crystal of dimension 0.2 millimeter and collect the data. Then, once you collect the data, the background intensities in the profile, peak profile of each Bragg reflection have to be subtracted from the peak intensities, and you have to apply corrections like Lorentz and polarization factor, and also absorption corrections, about which you are familiar in module 5. Since direct methods are used for overcoming the phase problem, one assumes point atoms. So whatever the intensities you get corresponding to spherical atoms have to be converted into the normalized intensity variable mod is. Already we have given the formula for that. So this corresponds to point atom. For the probabilistic estimates of the phase relationships, only those reflections with large E values yield better estimates, and hence after converting the intensity of HKL to the square of the normalized HF factor amplitude, here we use Wilson plot to make use of the thermal factor. These E's are sorted from larger to smaller values, and usually the E values up to 500 reflections are selected for generating the phase relationships. Here we come to an important step known as convergence map. Among the top 400 or 500 strong E values selected, the reflection serials HKL along with the symmetry transformation also have to be used to generate structure invariants, say triplets, phi h plus phi k plus phi l, such that h plus k plus l equal to 0. For example, among the 500 refractions, the first refraction can be taken as capital H, a second refraction can be taken as capital K, and the third refraction capital L is searched among the 498 remaining reflections and their symmetry transformations to obtain a reflection L such that H plus K plus L equal to 0. This is possible because these indices can take positive, negative or 0 values. As I told in the beginning, capital H I mean a 3 set of integers H1, K1, L1, by capital K, H2, K2, L2 and capital L, H3, K3, L3. The position of the K reflection is then shifted and the process is continued. So this computer is very easy. These triplets were then noted down. Then the process continues by treating the second reflection as H, third reflection as K, and L is searched among the 499 reflections and their transformation. At one stage, the first reflection may be the 450th reflection, and K may be the 451st reflection, and L is searched among the last 9 reflections and the transformation. So this is how the convergence map works. In the above process, the chances of getting triplets are more when the H and K occur at the top of the list. Thus, when you look into the output of the triplet forming reflections, then this will be the shape of a cone where more triplets will be found at the top of the list and less reflection will be found at the bottom, because the list is converging from largest to smallest value as the above steps are followed. But if you look at the bottom of the list, they contain reflections which will mostly occur when the H and K occur not only at the top but also at the middle of the sorted reflection list. And hence, the reflections occurring at the bottommost list in the convergence map are the frequently occurring reflections in the triplet, because we are talking about a triplet as a three-phase structure invariance phi h plus phi k plus phi l when h plus k plus l equal to 0. So now, in this triplet phase sum, I am going to use two phases of known values to obtain the third phase value. I already know what is the probable value for the triplet phi h plus phi k plus phi l. So now, when you use the reflection in such a way that they occur in maximum number of triplets, so new phases you can find maximum number. So that is why we use the bottom of the convergence list to select reflections and assign some known values to them. So now we talk about another step known as divergence map. So here, from the bottom of the reflection, we select a few reflections and assign them known phase values 0 or pi, and knowing the probable value for the triplet and knowing these two phases, third phase can be found out. So this is the principle of divergence map. So starting from a small bunch of reflection, we are going to get the phases for remaining bulk of reflection. That is why it is known as divergence map. Direct methods mainly use the Say's equation of sign relationships, that is, sin of h times sin of k times the sin of L is probably positive. And this is mostly used for centrosymmetry case as sin of h times sin of k is nearly equal to sin of h plus k. The nearly tells you that since you are using probability, nothing is exact. So, for non-centrosymmetry case, we have the relation phi of h plus phi of k is nearly equal to phi of h plus k. So, what it tells you is that, suppose you know the phase of reflection h and phase of reflection k such that h plus k plus l equal to 0, then phase of h plus k is simply phase of h plus phase of k. Whenever this h, k, l reflection have strong e values, we can approximate the L reflection to be equal to h plus k, because they follow the relation h plus k plus L equal to 0. Thus, knowing the signs of two reflections in the Say's equation or the phases of two reflections, the sign or the phase of third reflection can be obtained. Since the bottom serials in the convergence map contain the well-linked reflections that occur in most of the triplets, these reflections are chosen and assigned some phase values a priori like 0 or pi, and this is known as selecting reflections for origin fixing. So we will deal more about this in few minutes. In the divergence map, Knowing a small set of reflections which occur in maximum triplets, phases are assigned to them, and using phase relationships, unknown phases can be found with the knowledge of these origin-depending reflections. Thus, in the divergence map, the initial set of reflections may be very few, say for example 5 reflections with their phase values known, which is assigned by the user. This should be slowly expanded as more and more new reflections will be phased. This is the reason why this procedure is known as divergence map. The phases of large number of E's are obtained, and hence the E map or the Fourier map with mod E's and phi's used as coefficient can be computed. Since the number of reflections chosen for origin definition should be at least 4 with multiple choices of their phase values, and with an additional reflection by inertium of fixation, there are totally 2 power 5 starting sets possible. That is why it is known as multiple solution. Direct methods are of multi-solution in nature, but single solution can be chosen using figures of merit calculation. If 4 zonal reflections are chosen with phases 0 or pi as known, which are called origin defining reflections, and one more reflection for inertium of fixation is chosen with phase value plus or minus pi by 2. Now one has 5 reflections, each reflection having 2 choices for phase values. So totally we have 2 power 5 combination, 32 combinations of the starting 5 values for the phases. So accordingly we have 32 sets of solution given by direct methods. But of course the best solution can be picked up by the term known as combined figure of merit, and only for this solution E map is printed. So now this is the reason why direct methods are called multi-solution in nature. That mul stands for multi-solution. We use tangent formula to obtain individual phases phi HKL from the phase invariants. So tangent formula abbreviation tan is used. So together the first computer program name was given as MulTan, multiple solution. Direct methods is used along with tangent formula to give out the structural information. Depending upon the starting values for the phases, from each of these multiple choices of origin fixing reflections, the phases of remaining bulk of reflection can be calculated. They did it initially with the hand. That is why known as hand propagation or sign propagation and so on. In order to choose the best set of phases, as I told you in the beginning, figure of merit calculation is usually carried out. For example, if you use Multan program coming out from University of York, England, the best set is the one which has the largest value for the combined figure of merit termed as CFOM. But if you use the Shellx program released by Professor George Sheldrick from Germany, the best set is the one which has the lowest CFOM. So now we remember that the CFOM or the combined figure of merit the term used by Professor Wolfson's group in Multan program and Professor Shelley's group, the Shellx program, are not the same formula. That is why one formula CFOM has to be the largest in Multan. In Shellx says CFOM for the best set should be the lowest. Don't have any confusion. It is only for this best set, CFOM set, the E map will be printed by the program. It's E map in atomic like a graph, no? The atomic peaks will be printed. When I was doing the PhD in 80s, we used to connect each peak, and you can by line draw the line and mark the bond length and bond angle, everything. Now it is automation. So if you feed the peaks, we get the 3-dimensional picture on the screen within 1 minute. This is an important part in the field of direct methods. How to choose origin defining reflections. What should be the parities of those reflections? So to do that, let us consider what are the reflections having different parities. If you just do that, there are 8 parities possible for any general reflection HKL. The H can be even, K can be even, L can be even. This is denoted in the table, the first row in the header. E type parity or odd even even. Odd is denoted as O, or even odd even, even odd, odd even, odd even odd, even odd odd. So this even or odd denotes in the order HKL reflection. Now if you look into the down column, we have choices of origin. As we have seen before, there are 8 centers of symmetry in the unit cell. These are denoted by 0, 0, 0 origin, half 0, 0. This is the midpoint of the A axis, 0, half 0, midpoint of B axis, 0, 0, half midpoint of C axis, half 0, midpoint of the AB phase. 3 sets of phases are there. Then half 0, half, midpoint of the AC phase. Then midpoint of the BC phase, 0, half, then body center, half. Now the question is, I am going to assume a positive sign for all these reflections having 8 different parities corresponding to origin 0, 0, 0. My question is to see how the sign will change when you move from one origin to another. So there is a bookwork for that. So that has been done in the field of direct methods. So when you do the detailed chapter direct method, you know how to do it. Whenever the origin is moved from one point to another, there will be a phase factor occurring. For example, if the origin is moved from 0, 0, 0 to half 0, 0, the extra phase factor is minus 1 power h. So now we are trying to fill up the second row by looking into the parity of h reflections given in the header. First h reflection parity is even, therefore minus 1 power h will be plus. So I am putting plus in the second row. Now, if you go to the next element, h parity is odd. Therefore minus 1 power h is minus. Third, minus 1 power even plus. Fourth, minus 1 power even plus. Fifth, minus 1 power odd minus. Again 6, minus 1 power odd minus. Minus 1 power even plus. Then minus 1 power odd minus. So now I am filling the second row. So this tells you that when I move from 0, 0, 0 origin to half 0, 0, how the sign changes. Similarly, when 0, 0, 0 to 0, half 0 point is moved, now the translation is along the y-axis. Phase factor will be minus 1 power k. So now you are looking to the parity of k only in the 8 parities. No? So whenever the k is even, the sign will be plus. Whenever it is odd, it will be minus. So that also we are filling it here. So we get the third row. So like that for 0, 0 half change, phase factor minus 1 power L. So only when L is even it is positive, when L is odd it is minus. So that we are filling the row. Now when you talk about the change of origin from 0, 0, 0 to half 0, 2 phase factors will be there. So total phase factor minus 1 power h plus k. Now you have to look into the parity of h plus k given here. For example, even, h plus k will be even, therefore sign is plus. Whereas second reflection, h plus k will be odd plus even, that is your odd plus even, sorry, minus, therefore odd number minus. So if you look into the other reflection, even plus odd, that is odd, so minus. So similarly, you can fill up the next row, and so on. So now the question is, can you take for origin definition 3 reflections belonging to even parity? What I mean by origin definition is, I choose some reflections and assign some signs such a way that if the origin is shifting from one to another, at least for one of the reflections, the sign should change. This is known as unique fixing of origin. Now, if I say I can take origin, defining reflection from even parity, all the 3 reflections, there is ambiguity. So the sign of the even reflection is positive not only for 0, 0, 0, for all the other 7 shifts also. In other words, the total number of ambiguity is 8 if we choose all definition from even parity for origin definition. But you can choose only one reflection from even parity. Now you can take another reflection belonging to odd even parity. Now if you see, for 0, 0, 0 origin, both the reflections are plus. But when you go to 0, half 0, again both the reflections are plus sign. 0, 0, half, again both are plus. 0, half origin, again plus. So now the signs of these 2 reflections are plus, not only for 0, 0, 0 origin, but also for 3 more origins, which means that ambiguity is 4 now. Of course, we have reduced the ambiguity from 8 to 4. Now you take one more reflection, even, odd, even, and assign the sign to be plus. Now, you see in how many cases of origins, all the 3 are plus, only in 2 cases, namely 0, 0, 0 and 0, 0, half. So now you say the ambiguity has reduced to 2. So slowly from 8 we reduce the ambiguity to 4, then 4 to 2. Now we take one more reflection of the parity even, even, 0 and assign a sign. We just see all these 4 parity reflection, that is even, 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 odd, even, 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 odd, even, even, odd, will be plus only for the origin 0, 0, 0. Now I say it is origin is uniquely fixed, because we just see when the origin is moved, at least for one of these reflection, the sign will change. So now what you do is, at the bottom of the convergence list, you take 4 reflections belonging to this parity and assign some sign. Then you proceed further to get the sign of the other reflection for centrosymmetric case. So this is the way. Since it has been done by hand, this is known as hand propagation method. Here we are going to see how the 3-dimensional structure is determined for a small molecule. So I am just giving a demo of this the suit SHELX program written by Professor George Sheldrick. This SHELX S is used to determine the structure using direct methods, and SHELX L is for doing the refinement, adjustment of parameters like position and thermal factors to get a better agreement between the model you propose with the actual structure. This last word S stands for such a solution in SHELX S, and last letter L in SHELX L stands for least square refinement. So usually the plotting is done by the program RTEP. The PC version has been done by Professor Zolnoy, and the name is ZRTEP. All these programs are available in a suite known as WinGex, and it can be got freely once you write to the authors. Now, this SHELX program expects the user to provide 2 files. One is the intensity data file called star.html, and another file known as star.ins, instruction file. The instruction file consists of the title of the compound, cell parameter including the wavelength at which data is collected, the cell edges ABC in angstrom unit, and the corresponding angles alpha, beta, gamma in degrees. This is followed by the number of molecules in the unit cell denoted as Z, and the standard deviation of the 6 cell parameters. After that, the lattice detail is given. For each lattice there is a number. For primitive lattice, the number is 1. Suppose your space group is non-centrosymmetric, you have to attach a negative sign with this, otherwise you just leave it as such. Now, this is followed by another instruction, namely SFAC. What are the scattering factors, elements present there? Carbon, hydrogen, oxygen, nitrogen. Then is followed a letter unit. In the unit cell, how many atoms are there belonging to each species? Now, in the card on SFAC, you can change the order anywhere, but accordingly in the unit also you have to write. Suppose you write H in the first instance of carbon, in the unit cell, first number will be total number of hydrogens in the unit cell. So then trough is there. By giving trough you mean tangent refinement. So the program will invoke direct methods option to do the such analysis. Suppose if you have one heavy atom or 2 heavy atoms, then you can use Patterson method by giving command PATT. So this is a way. Then there is a command HKLF4 denoting what type of data you have collected, whether it is the middle indices HKL, intensity is I, and standard of intensity sigma of I, or HKL, mod F, and sigma of mod F. Okay, this is the thing. So now as an example, we are going to see these 2 files in the next projection. We have whatever files necessary for the SHELX S to run. Whatever is there, I told you just now. Title is filled up, cell is filled up, Z error is filled up, lattice is filled up, SFAC is there, unit is there, trough is there, HKLF4. Then last card is end. Then at the bottom I have given the example of a reflection file. We just see here that the middle is HKL can be positive, negative, or 0. The last reflection in this file is indicated to the computer program by typing 000 in all the places. Now with the availability of these 2 files, SHELX S97 can be run. The 97 indicates the program version in the year 1997. So these 2 files are sufficient to run the program. The program takes just less than 5 seconds to get the peaks. So if you look at the figure, I given a table. The last column denotes the electron density values for the peaks. If you look at the peaks, all are assumed to be Q. As I told you in the beginning, direct methods assumes equal atom types. If you look at what types of atom it has taken, next to Q1, you just see 1111. This is known as species identifier. Now you go to SFAC card and see what is the first species, carbon. So the program has assumed all atoms to be equal, which is equal to carbon. Then it has found the fractional coordinates, because these coordinates are usually less than 1 and some positions are greater than 1. I already told you what do you mean by a fractional position atom having fractional coordinates greater than 1. It has peeped into the next unit cell along the direction to compensate that another atom will peep in the unit cell. So that's it. This program, if you look at the last column, these are the electron density maxima. We define there's an atom because there's the electron density maximum. If you look here, the structure which you are given consists of 20 atoms only. If you look at the electron density values, up to 20 atoms, a regular decrease is there. After 20, a sudden jump is there. So we select up to 20 atoms, then we can plot the atoms and so on. Then these positions are only rough positions, so which can be adjusted by a slight movement of delta x plus or minus and so on, delta y and delta z. Here you see a factor 11. In this program, whichever value do not want to be adjusted or refined, you have to add 10 with that, which means that you have already a value of 1. This is known as occupancy. So since all atoms scatter with the full occupancy, you need to adjust it. After that, you are given a 0.05. The output is ready to be submitted for another job, least square refinement. Here we are assigning thermal factor. Even though the assumption made by Hoffman and Kahl assume non-vibrating point atoms, once the structure is obtained by them, you can assume thermal factor 0.05. So even though you give equal thermal factor for all the atoms, depending upon the neighborhood atoms, some atoms may vibrate more, some atoms will vibrate less. So now with this modification, one can submit the job for ShellX L. Now whenever you have the model, actually the coordinate system ShellX file can be used as a plotting program by using the program Platon available in WinGX. So now ShellX L97 we are going to run after viewing the molecule, and we are going to adjust 3 positions of each atom and also 1 thermal parameter. Totally 4 parameters are going to be adjusted. Since the 20 atoms, 20 times 4 is 80 plus 1 scale factor. 81 parameters are going to be adjusted. So this is known as isotropic refinement, because we assume the vibrations to be same, that is iso, along x, y and z direction. This will also take only some seconds to come to a convergence. After convergence, the refinement is stopped. What is convergence? Between one cycle to another cycle, this weighted R will be shifting. Between 2 cycles, if it remains same, it means the convergence has been reached. You have to stop it or change the procedures of the refinement. For example, from isotropic refinement, you can go to anisotropic. Isotropic means you assume the same vibration along all the directions. Now we assume that vibrations are different in each direction and so on. So after the convergence, the refinement is stopped. Usually this happens within 10 cycles. Then anisotropic refinement will be started with the output file renamed as the instruction file with the inclusion of the command ANIS, meaning anisotropic. Now we have the original X, Y, Z direction in which vibration will be assumed to be unequal, and also your 3 more directions will be there. Cross direction between XY, between YZ, between ZX axis. Totally along 6 directions movement are considered. So your vibration picture will be not like a sphere in iso, but in anisotropic it will be ellipsoid. So here, as I said, instead of assuming the thermal vibration to be same in all the 3 directions as in the isotropic refinement, in anisotropic the vibrations are assumed to be different, not only along the 3 directions x, y, z, but also vibrations are considered along the cross direction x, y, y, z, z, x. So 6 directions are considered. So if you do the plotting called thermal plot, which is done by the program originally developed by Professor Johnson, which is called RTEP, Oak Ridge Thermal Ellipsoidal Plot, we can see the ellipsoids representing the anisotropic thermal vibration. So after convergence, usually the R factor will come down 10% or less. Nowadays it's quite possible to have even 3 or 4% because the data collection facility is very great, and very good diffracting crystals are there. Now, finally, we have to determine the hydrogen atoms. So far, we determine only the non-hydrogen atoms. Now, hydrogens are also there. Maybe 20 or 25 hydrogens are there. They also substantially contribute to the intensities. So now, to do that, you can do a Fourier called difference Fourier method by feeding in all the known part and get the unknown part, hydrogen. But usually the referees request you to geometrically fix it, no? So we can have a program called, the same program we have a provision called hfix command, and using which you can geometrically fix the hydrogen, and the final R factor, as I told you in the beginning, can be up to 5% or lesser. For a well-refined model, the goodness of its goof factor should be around 1, and the mean shift bar ESD during refinement should be close to 0. The scale factor is denoted in the program by FVAR, and L dot S denotes number of least square cycles to be used. Usually 10 is sufficient. FMAP2 denotes the different Fourier map. Suppose you want to see whether there is any extra atom is coming out, you can do this with this command, and you got to give how many atoms you want to see by giving plan 10, 20 and so on. This is known as difference Fourier. Then once you get these things done after anisotropic refinement, then you can fix the hydrogen atom. Because hydrogen atoms are very light, all hydrogen will not appear in the difference Fourier. We can give the geometrical fixing. There is a means of giving hfix command depending upon what type of hydrogens are there, NH or NH2 and CH3 and so on. Once you do it, then we get the results about the reliability of the model you are proposing for the actual structures. Now, in every cycle of refinement, an R factor is printed. That is known as WR2, weighted R factor based on square of the intensity differences. Finally, we have the R factor, which is nothing but summation over absolute of the mod F4 minus mod Fc divided by summation over mod F4. So this tells you how far your calculated structure factors agree with the observed structure factors. Smaller the difference, better is the agreement. So smaller the R value, you should have more happiness, because usually for small molecules R factors up to 3 to 4% are now possible. When I say R factor is 4%, the discrepancy is 4% and the reliability is 96%. So that is how you have to interpret R factor. R factor is calculated for two types of data, one with full data, another with reflections with I greater than 2 sigma I only. So when you have this cutoff data, R factor will be smaller for that than the one with full data. Once you have this everything done, then the final res file can be used as input to the program written by Professor Nardelli called PAST to calculate the intermolecular features and intramolecular features. Intramolecular features, I mean bond length, bond angle, torsion angles. By intermolecular features, I mean hydrogen bonds between the symmetry related molecules and so on. Again, the final thermal plots can also be done using a Platon. With these results, one can submit the research findings as a publication to the crystallographic journals. So, students, let us summarize what we have learned in this module. A historical introduction was discussed here. How to overcome the phase problem using direct methods, and all aspects of the procedures are explained, because this is a Nobel Prize winning topic, and Professor Hoffman and Karl have contributed substantially in this field, for which they have been honored with the Nobel Prize. And of course, another reason being I did my postdoctoral training for 4 years under him. So I had a pleasure in popularizing his field of interest. The practical way of determining the three-dimensional structure of a small molecule with direct methods and refining it using the softwares are also detailed from the beginning to the end. Of course, these softwares are free only, no problem.